In the last session, we were discussing the half-life topic. Now we are doing some questions related to the half-life. So bismuth 214 is a radioactive and it is having a half-life of 20 minutes. So means after every 20 minutes, it becomes half of its original value. The count rate from a sample of a bismuth is 360. Like right now, 360 radiations are coming out from the sample. We have to predict the count after 60 minutes. So if the half-life is 20 minutes, how many half-life should pass to reach this 60 minutes? So it means 3 half-lives should be there. Because if one half-life is 20 minutes, 3 half-lives mean 60 minutes. So originally now we have 360. So after the half-life means after 20 minutes, how much sample will be active emitting out radiation? Half of 360 is 180. Then after another half-life, means after another 20 minutes, total time passed will be 40. But after another 20 minutes, it will be 90. And then after another half-life, again 20 minutes passed, so it will be half of its original value. So half of 90 is 45. So how many half-lives have passed? 3 half-lives passed. And what is the total interval when 360 changed to 45? So it means the total duration will be 60 minutes because 20 plus 20 plus 20. So after 3 half-life or after 60 minutes, it will, the 360, the original sample was 360, but now we are left with only, like original sample was emitting out or giving out 360 radiations per second, but now it will only give 45 counts per second. Then another question. In the question, we have a radon, which is having a half-life of 3.8 days. Means after every 3.8 days, it will become half of its original value. At a certain time, we have 6.4 into 10 to the power 6 radon nuclei. Calculate the number of alpha particles emitted by radon nuclei in the following 7.6 days. So radon is emitting out alpha particles. So basically, we want to find how much is because the question is calculate number of alpha particles emitted. So in the beginning, all 6.4 into 10 to the power 6 is emitting out radiation because all is active, or we can say unstable or active, we can also say. Then after half-life, so we have 6.4 into 10 to the power 6 atoms which are radioactive, which are emitting. Yeah, that's true. So basically, as you can see, in 7.6, basically 2 half-lives are there. So first, after first half-life, because these are the nuclei, that's why we're dividing into 2 halves. Before radiation was there, so it always become half. In a nuclei, half becomes stable, half become unstable. So what is half of 6.4 exponent 6? So half is 3.2 into 10 to the power 6 will be unstable. And 3.2 into 10 to the power 6 will be stable. So stable one means they already emit out radiation. They give out alpha particle. Then what happened? So how much interval have passed? Because this always happened after the half-life. So after the half-life or after 3.8 days, this is what happened. Then because we want to find after 7.6 days, it means second half-life. So after another half-life, what will happen? The unstable one will further decay. And out of 3.6, the 3.2, 1.6 into 10 to the power 6 will be stable. Or you can say unstable. And half of this 1.6 into 10 to the power 6 will be stable. So that is after another half-life, which is 3.8 days. So total, because two half-lives are there, the question is calculate number of alpha particles emitted. So the stable one already emit out. They will not emit. Unstable are continue to emitting out, but stable one already emitted. Like they will not emit now. So how to find the total number of alpha particle emitted? It means how many atoms are stable. That is the total number of alpha particles emitted. So 3.2 into 10 to the power 6 here and 1.6 into 10 to the power 6. So total number which already emitted out the alpha particle, that is when we add these two numbers. So 3.2, first 3.2 is emitted out and then 1.6 emitted out. So what is the total number of alpha particles or the stable nuclei? That is equals to 4.8 into 10 to the power 6 will be the number of alpha particles emitted or number of the atom which become stable. Because unstable one is emitting out radiation. They continue to emit out radiation, but stable one, they emitted out the radiation and they become stable. So another question. Half-life of americium nuclide is 470 years. A sample contains 8 into 10 to the power 14 atoms. After some time, 6 into 10 to the power 14 atoms have decayed. Have decayed means this many become stable. Calculate the time required for this decay. So like how much time it will take when we will have left with 6 exponent 14 stable atoms. So in the beginning, and one half-life is 470 years. So how to work out this? In the beginning, we will have 8 into 10 to the power 14, which are undecayed. Undecayed means unstable. Then after the half-life, what happens? After the half-life, because it becomes half of its original value. So 8 exponent 14, half is 4 exponent 14. So 4 exponent 14 will be undecayed out of total. This will be undecayed. And 4 into 10 to the power 14 will be decayed. So this is like in the beginning, 8 exponent 14 undecayed, half will be undecayed, half will be decayed. Decayed means half are like decayed means the one which is stable, not emitting out more radiation, and one unstable that we call undecayed. So unstable one, so this is one half-life. So how many total, because we want to find when we are left with 6 exponent 14 undecayed atoms. So right now we have 4 exponent 14 undecayed atoms after one half-life. Then after another half-life, what will happen? This sample will further decay, the undecayed one. So we are left with 2 into 10 to the power 14 undecayed or unstable and 2 into 10 to the power 14 decayed. So how many total have decayed here till this point? And this is after another half-life. So how many total atoms have decayed? As you can see from the value 4 exponent 14 and 2 exponent 14. Like first 4 exponent 14 decade, then 2 exponent 14 decade. So how many atoms have decayed now? Till this point, 4 exponent 14 plus 2 exponent 14. So when we add, actually 6 exponent 14 atoms have decayed. And that was a question that when 6 exponent 14 atoms have decayed, how much time is required? So how much time is required? How many half-lives are required? 2 half-lives. So one half-life is 470 years. So one half-life is 470. So 2 half-lives will be 940 years. So it will take 940 years for this sample to convert or to change from 8 into 10 power undecayed atoms to 6 into 10 power 14 decayed atoms. So the definition, what is the definition of a half-life? Half-life means time taken by half of the radioactive sample to decay, or time taken by the activity to become half of its original value, or number of the atom become half of its original value. So a workman operates a machine that uses a beta particle to determine the level of the liquid in the plastic water bottle. Suggests why alpha particle is not a suitable. What is the reason why alpha particle? Because alpha cannot pass through a paper. So how alpha will pass through a plastic? So if a person is finding the water level by using the alpha radiation. So like example, a bottle is there filled with water, and a person want to determine the water level. He uses a source here and use a detector other side. So he's using a radiation, he's using a concept, and radiation is coming out from the sample. If the radiation from the source passes through and reaches a detector, it means water level is below. But if the radiation, like because if the water level or the liquid level is up or higher, then the amount of radiation which will pass, that will decrease. So it can identify that the level is not calibrated correctly or the container is not filled correctly. But why alpha particle is not a suitable source? Even liquid level, alpha particle won't change, because even liquid level is up, high or below, but alpha particle cannot penetrate or pass through the plastic. Like it cannot pass through a paper, how it can pass through a plastic? That's why alpha particle is not a suitable source. So why alpha particle is not a suitable? Because it can pass through. You can mention the walls of a container or the plastic. And why gamma is not suitable for this purpose? What is the reason? Because gamma radiation, even the water level is high or low, gamma radiation can be stopped by thick aluminum, thick lead. So even the water level is up or down, that does not make difference to the gamma, because gamma radiation is having a higher penetration, so they can pass easily. So why gamma is not suitable? Because gamma cannot be stopped by plastic or a paper or a liquid. That's why. So as a result, it cannot be stopped by the plastic or the liquid. So detector reading does not change. If we are using alpha, then it is not suitable because it cannot pass. If we are using gamma, it's also not suitable because it will pass, even the level is, any level is there, but it will continue to pass. So the most appropriate source in this example is a beta. Another question, a sample contain only one radioactive isotope which is brought in the lab. Half-life of the isotope is 15 hours. So after 15 hours, it becomes half of its original value. The sample is placed near the radiation detector. The detector is switched on after 1 minute, account 440. A sample is left to the detector, the experiment repeated 45 hours later. The detector is switched on for 1 minute. Predict the reading of the counts on this occasion. So how we can predict the reading on the count in this occasion? And in this question, remember, the background radiation as the part, one of the part, the background radiation from the surrounding is equals to 24. So what happened? That part, that is in the previous part, but because I did not include that in the question, so, but the radiation from the background or the background radiations are 24. So basically, when we place a detector here, so this is a detector and we place in front of the source, which is emitting out radiation. So detector is recording two radiation. One is from the source and another one is from the surrounding. So the total reading on the detector is 440. That is the total reading. And surrounding readings are 24. So the total reading on the detector is 440 and the background radiation are 24. So how much is coming from the source? So how much is the source radiation? So source radiation will be, because the total reading is equals to source reading plus the surrounding, or we can say background. The total reading on the detector is 440. The source reading we don't know, and the background radiation are 24. So 24 will move other side. So 440 minus 24. So it will be 416. So basically the source radiation or radiation from the source are 416. Now we want to find what will be the reading on the detector. Only the source radiation will become half, the background radiation does not change. So what will be the reading on the detector? So first we'll find, as they mentioned, the half-life is 15 hours and we want to find the detector reading after 45 hours. So right now the source radiation from the source, 416. These are the radiation from the source. So 15 hours and we want to find 45 hours. So basically how many half-lives we need? We need 3 half-lives. So after first half-life, after the half-life, half of 416. So this 416 divided by 2, which is equals to 208. Then after another 15 years or a half-life, the 208 will become 104. Then after another half-life, why 3 times? Because we want to find after 45 hours means 3 half-lives. So after another half-life, it will be 100 and half of 104, which is equals to 52. So the source radiation will become 52. So what will be, the question is, what is the detector reading? They're not asking what is the source reading. They're asking what is the detector reading. So what will be the detector reading on the detector? After 3 half-lives, first, the radiation from the source was 416. But now what happened? the radiation from the source after 3 half-life become 52. So 52 radiation from the source, and the background radiation does not change, more or less it remains same. So that is 24. So 52 radiations from the source and 24 due to the background. So what will be the reading on the detector? 52 plus 24, that is equals to 76. So reading on the detector is equals to 76. The ground count rate of a radioactive soap 30. So background counts here in the question, background counts are given 30. Means radiation from the surrounding are 30. A radioactive sample has a half-life of 50 minutes. Means after every 50 minutes, it becomes half of its original value. The sample is placed in a fixed distance from a detector. So look, again, the similar type of question, you have a source. So this is a source. So source is emitting out radiation, and there are radiations from the from the background surrounding as well. So when the detector records the radiations, the total radiation by the detector, as I mentioned here, the detector measures the initial count rate from the sample, including the background, is 310. So detector read 310. Out of 310, 30 radiations are from the background. So how many radiations are coming from the source? If 30 radiations are from background, so how many are coming from the source remaining? So 310 minus 30, which is equals to 280. So basically 280 radiations are coming from the source. So corrected counts here for the background means like we remove the background, we only include the source. So 280 here, 10 boxes equals to 50. So each box equals to 5. So this is 250, 260, 270, and 280. So this will be 280. So this is 280. That's the first point. The half-life, what is the half-life? 50 minutes. Means after every 50 minutes, it becomes half of its original value. So 40, each on x-axis, 10 boxes equals to 20. So each box equal to 2. So 42, 4, 6, 8, and 50. So means after half-life, after 50 minutes, it will become half. So what is half of 280? Half of 280 is 140. So this will be 110. Then basically this is 150. So 2 boxes below that will be 140. So this will be 140. So at 50, when the time is 50, this will be 140. So it will be here. Then again another 50 minutes, because after every 50 minutes it becomes half. So what is a half of 140? That is 70. So 50, 60, 70. So this is 70. So when it becomes 70, after further 50 minutes, so double, like 50 become 100, and this is 70. So 4 boxes above here. Then after another, like 35 will be there. Each box is representing 5. So 5 boxes. Sorry, 7 boxes will be there because we need 35. This is 10, 20, 30, 35. So, and 150, because this was 100, then 150 will be here. and this will be 35 7 boxes. So 1, 2, and 3. So we join these points. So we'll join these points to show the variation of the counts, the corrected counts from the source. So it will be a freehand. You have to join as a freehand, or it should be a curve. Is it clear, this question? How we work out the amount of radiation after every half-life? Then a radiation detector is set up in the lab where there is no radioactive sample. So then no radioactive sample, it will detect the radiation from the surrounding. 6 separate occasions, we measure the radiation 23, 27, 25, 24, 20. So why the readings are not identical? Because this is a random process. Like sometime more radiation, sometime less radiation. That's why we don't have a fixed number. It can be a bit more, bit less, and suggest a possible source of background. So what could be a source? So you can mention rocks, you can mention building, earth, cosmic radiation, nuclear waste, or maybe radon gas. Then to ensure the safety of the worker in the lab where the radioactive sources are used, and describe how the material, we'll discuss this part, how it will be stored. And this question we already discussed in the last session. So today we mainly discuss the half-life questions, the radioactive emission, and the half-life questions. Any question or a doubt related to the session today?